A beam of light from a distant galaxy takes millions of years to reach our telescopes. In that time, civilizations could rise and fall, species could evolve and vanish, continents could drift across planets we'll never visit. Yet when that light finally arrives, it carries a mystery so profound it shook the foundations of physics itself. Galaxies spin. They rotate like cosmic pinwheels scattered across the universe. And by every law of physics we understand, they shouldn't exist. The stars at their edges move so fast they should have been flung into the void billions of years ago. Galaxies should have torn themselves apart before life ever had a chance to begin. But they didn't. They're still here, rotating peacefully, defying explanation. For decades, this was one of the deepest puzzles in all of science, and now we may finally understand why. If you're interested, subscribe, hit that like button, and let's explore this cosmic mystery together. To understand why galaxies shouldn't exist, we need to start with something simpler, something familiar. Think about a ball on a string. Spin it around your head fast enough, and you feel tension in the string. That tension is the only thing preventing the ball from flying away. The faster you spin it, the stronger that pull needs to be. If the string breaks, the ball shoots off in a straight line, no longer bound to its circular path. This is not opinion or theory. It's fundamental physics, confirmed billions of times in everyday experience. Now scale that up. Replace the ball with a planet. Replace the string with gravity. A planet orbits a star because gravity provides exactly the right pull to keep it in motion without flying away or falling inward. The mathematics is elegant and precise. The closer a planet is to its star, the faster it must move to maintain a stable orbit. The farther away, the slower. This relationship is ironclad. Mercury, closest to the Sun, races around at nearly 48 kilometers per second. Neptune, far out in the cold darkness, crawls along at just 5 kilometers per second. The pattern is universal, mathematical, and seemingly unbreakable. This same logic should apply to galaxies. A galaxy is, at its most basic level, a collection of stars bound together by gravity. The center contains the densest concentration of mass, primarily a supermassive black hole surrounded by billions of tightly packed stars. The outer regions are sparser, less massive, stretched thin across vast distances. If gravity is the string, and stars are the objects being spun, then the rules should be identical to planetary motion. Stars close to the galactic center should orbit quickly. Stars far from the center should orbit slowly. The relationship should follow the same mathematical curve we see in solar systems. Predictable, reliable, absolute. But when astronomers first measured how fast stars actually move in galaxies, something was wrong. Deeply, fundamentally wrong. The stars near the center behaved as expected. Their speeds matched predictions perfectly. But as measurements moved outward, toward the galactic edges, the numbers stopped making sense. Stars that should have been crawling along at modest speeds were racing. Stars so far from the center that they barely felt the galaxy's gravitational pull were moving just as fast as stars much closer in. In some cases, they were moving faster. This was not a small discrepancy. It was not experimental error or a quirk of one unusual galaxy. Every galaxy observed showed the same behavior. The rotation curves, as they're called, remained flat far beyond where they should have dropped off. Stars at the edge moved with velocities that defied every calculation. And here's the critical point. At those speeds, they should not be bound to the galaxy at all. The gravity from all the visible matter, every star, every cloud of gas, every planet and asteroid and speck of dust, was not nearly strong enough to hold them. They should have been flung into intergalactic space long ago, leaving galaxies as small, dense cores surrounded by emptiness. Yet galaxies endure. The Milky Way has been rotating for over 13 billion years. Andromeda, our nearest large neighbor, has spun through space for just as long. Billions of galaxies scattered across the observable universe, all rotating in defiance of the physics that governs everything else we know. This was not just a puzzle. It was a crisis. Because if our understanding of gravity was wrong, then everything built on that understanding, from planetary motion to the structure of space-time itself, would need to be reconsidered. For a while, scientists searched for errors. Perhaps the mass estimates were wrong. Perhaps there were more stars than we could see, hidden in the darkness between galaxies. Perhaps our telescopes missed faint populations of dim stars or dense clouds that contributed mass without emitting light. Teams recalculated, reobserved, refined their instruments. The discrepancy remained. In fact, it grew worse. The more carefully galaxies were studied, the more obvious it became that visible matter, everything we can see and measure directly, accounts for only a fraction of the mass needed to explain what we observe. This is where the story begins to turn strange, because the solution, if it can be called that, required accepting something almost unthinkable. The universe contains mass we cannot see, not because it's hidden behind something else or too faint for our instruments, but because it does not emit, absorb, or reflect light at all. It interacts with nothing except through gravity. It has no temperature, no color, no electromagnetic signature of any kind. It is invisible in the most complete sense possible. And it outweighs all the stars, planets, and gas clouds in the universe, combined by a ratio of more than 5-to-1. This unseen mass was given a name that captures both its presence and its mystery: dark matter. Not dark because it's shadowy or obscured, but dark because it is fundamentally undetectable by any means except the gravitational influence it exerts. It does not shine. It does not block light. It passes through ordinary matter as if matter weren't there. Yet it shapes galaxies, bends space-time, and governs the structure of the entire cosmos. Without it, galaxies would not exist. Without it, the universe as we know it could not have formed. The idea sounds absurd at first. Invisible matter filling the universe? An entire category of substance that interacts with reality only through one of the four fundamental forces? It feels like inventing an explanation to patch over ignorance. Like medieval astronomers adding epicycles to preserve Earth-centered cosmology when the evidence was screaming that the model was wrong. But dark matter is not a desperate patch. It is a prediction that emerged from observation, confirmed independently across multiple lines of evidence, and integrated into our understanding of cosmology so deeply that removing it would collapse decades of progress. Still, the question persists. If dark matter is real, what is it made of? Where did it come from? Why does it behave so differently from everything else? And most importantly, can we ever detect it directly, or are we forever limited to inferring its existence from the way it shapes the visible universe? These questions remain unanswered. They sit at the frontier of modern physics, pulling researchers into experiments deep underground, into particle accelerators, and into observations of the faintest signals from the edge of the cosmos. The rotation of galaxies was just the beginning. It opened a door to a universe stranger and more complex than anyone imagined. The first serious hints that something was wrong came in the 1930s, long before the term dark matter entered common use. A Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a massive collection of galaxies bound together by gravity. He measured how fast individual galaxies were moving within the cluster and used those speeds to estimate the total mass holding them together. The numbers didn't match. The galaxies were moving far too quickly. If the only mass present was what could be seen in stars and gas, the cluster should have flown apart long ago. Zwicky calculated that there had to be hundreds of times more mass than was visible. He called it Dunkle Materie, German for dark matter. At the time, the idea was largely ignored. Zwicky was known for unconventional thinking, and his estimates involved significant uncertainties. Other astronomers assumed the discrepancy would resolve itself with better data or refined models. It didn't. Decades passed. Technology improved. Observations became more precise, and the problem only grew more pronounced. In the 1970s, astronomer Vera Rubin conducted detailed studies of galaxy rotation curves. She focused on spiral galaxies, measuring the velocities of stars and gas clouds at various distances from the galactic center. Her work was meticulous, rigorous, and undeniable. The rotation curves were flat. Stars at the outer edges moved just as fast as those closer in, sometimes even faster. There was no drop-off, no decline in velocity with distance. Every galaxy she studied showed the same pattern. Rubin's findings could not be dismissed. They were too consistent, too well documented, and too widespread. The visible matter in galaxies, all the stars and gas we could observe, accounted for only about 10% of the mass needed to explain the rotation speeds. The remaining 90% was invisible. It had to be there, exerting gravitational influence, but it emitted no light and interacted with nothing electromagnetically. This was not a fringe claim from a single researcher. It was reproducible, verifiable reality. The implications were staggering. If galaxies contained this much unseen mass, then our picture of the universe was fundamentally incomplete. The glowing stars and nebulae that fill our telescopes represented only a tiny fraction of what existed. The rest was hidden, woven into the structure of space itself, shaping everything we saw without revealing itself directly. At first, physicists explored conventional explanations. Perhaps the missing mass was made of ordinary matter that simply didn't shine. Brown dwarfs, for instance, are objects too small to ignite fusion, but still massive enough to exert gravity. Perhaps galaxies were filled with countless brown dwarfs, invisible to telescopes but contributing significant mass. Or perhaps black holes scattered throughout galaxies accounted for the discrepancy. Or vast clouds of cold gas, too diffuse to radiate but substantial enough in total mass to matter. These ideas were tested. Searches for brown dwarfs found some, but nowhere near enough to explain the missing mass. Black holes existed, but their numbers and masses fell far short of what was needed. Cold gas clouds could be mapped through radio observations, and while they contributed, they couldn't close the gap. No matter how creatively physicists reinterpreted the visible components of galaxies, the conclusion remained the same. The missing mass was not ordinary matter hiding in darkness. It was something else entirely. This realization forced a conceptual shift. The universe was not just bigger than we thought, it was stranger. It contained substances and structures that operated outside the familiar framework of atoms, light, and electromagnetic forces. The periodic table, the foundation of chemistry and much of physics, described only a small subset of what existed. Dark matter belonged to a different category, one that followed different rules and interacted with reality in fundamentally different ways. The name itself, dark matter, is almost misleading. It suggests something shadowy or obscured, as if shining a brighter light might reveal it. But darkness in this context is not about visibility. It is about interaction. Ordinary matter interacts electromagnetically. Atoms absorb and emit photons. Electrons scatter light. Chemical bonds form because charged particles attract and repel one another. This electromagnetic interaction is what allows us to see, touch, and manipulate the world around us. Dark matter does none of this. It has no charge. It does not couple to photons. It passes through electromagnetic fields without responding. Yet it has mass, and mass curves space-time. This is the one thread connecting dark matter to the visible universe. Gravity, unlike electromagnetism, acts on all forms of mass and energy equally. Dark matter feels gravity and exerts it. That single interaction is enough to shape galaxies, bend light, and dictate the large-scale structure of the cosmos. It is enough to explain why galaxies rotate the way they do, why galaxy clusters hold together, and why the universe evolved from a smooth, featureless state into the rich tapestry of structures we observe today. But it is not enough to detect dark matter directly, because gravity is weak, extraordinarily weak compared to the other fundamental forces. To measure the gravitational influence of a small amount of dark matter requires observing its effect on enormous masses over vast distances. In a laboratory, the gravitational pull of even a large object is negligible. Dark matter particles, if they exist, could be passing through your body right now by the billions, and you would never feel it. They would interact with nothing, disturb nothing, leave no trace except the faintest warping of space-time too subtle to measure at such small scales. This creates a profound challenge. How do you study something that refuses to interact? How do you confirm the existence of particles that leave no signal in any detector ever built? The answer lies in accumulation. While individual dark matter particles may be invisible, their collective influence is undeniable. And that influence shows up not just in galaxy rotation curves, but in a dozen other independent observations scattered across the cosmos. One of the most striking confirmations comes from gravitational lensing. When light from a distant galaxy passes near a massive object, the object's gravity bends the light's path, much like a lens bends light in optics. This effect was predicted by Einstein's general relativity and confirmed observationally in 1919. Astronomers use it routinely to map the distribution of mass in the universe. By observing how light from background galaxies is distorted as it passes through galaxy clusters, they can reconstruct where mass is concentrated, even if that mass emits no light. The results are unambiguous. The mass responsible for the lensing extends far beyond the visible galaxies. It forms vast halos, invisible but gravitationally dominant, surrounding clusters and bending light in ways that only make sense if dark matter is real. In some cases, collisions between galaxy clusters have separated the dark matter from the ordinary matter, creating regions where the lensing signal and the visible galaxies no longer align. These collisions act as natural experiments, demonstrating that dark matter and ordinary matter can be pulled apart because they interact differently with their surroundings. One of the most famous examples is the Bullet Cluster, where two galaxy clusters collided at immense speeds. The ordinary matter, primarily hot gas, slammed into itself and slowed down due to electromagnetic interactions. The dark matter, immune to such interactions, passed through unimpeded. Gravitational lensing revealed that the majority of the mass was not where the gas ended up, but where the dark matter coasted through. This observation alone is difficult to explain without invoking dark matter. Alternative theories that modify gravity rather than adding unseen mass struggle to account for this clean separation. Another line of evidence comes from the cosmic microwave background, the afterglow of the Big Bang. This faint radiation fills the universe, a relic from a time when the cosmos was hot, dense, and opaque. Tiny fluctuations in its temperature map the seeds of all structure that formed later. The pattern of these fluctuations depends sensitively on the composition of the universe. How much ordinary matter exists, how much dark matter, how much dark energy, all of these influence the peaks and valleys in the temperature map. When the cosmic microwave background was measured with extraordinary precision by satellites like WMAP and Planck, the data revealed a universe composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. These numbers are not guesses. They are the result of fitting theoretical models to observations with such accuracy that the uncertainties are astonishingly small. The agreement between prediction and measurement is one of the great triumphs of modern cosmology, and it confirms beyond reasonable doubt that dark matter is real and constitutes the majority of the mass in the universe. Even the formation of galaxies themselves depends on dark matter. In the early universe, matter was distributed almost uniformly. Almost, but not quite. Tiny density fluctuations, imprinted during the first moments after the Big Bang, acted as seeds. Regions slightly denser than average attracted more matter through gravity. Over time, these regions grew, pulling in surrounding material and collapsing into the structures we see today. But there's a problem. Ordinary matter alone cannot form galaxies fast enough. In the early universe, ordinary matter was coupled to radiation. Photons bounced off electrons, creating pressure that resisted gravitational collapse. This pressure prevented ordinary matter from clumping together efficiently. If galaxies had to form from ordinary matter alone, the process would have been too slow. The universe would look very different today, smoother and less structured than what we observe. Dark matter solves this problem. Because it does not interact electromagnetically, it feels no radiation pressure. It began collapsing into clumps immediately, long before ordinary matter could follow. These dark matter halos grew first, creating gravitational wells that ordinary matter eventually fell into. Stars and galaxies formed within these pre-existing structures, sculpted by the invisible scaffolding of dark matter. Without it, the universe would be a formless sea of gas, starless and lifeless. This picture, where dark matter provides the gravitational framework for galaxy formation, is now the standard model in cosmology. Simulations of structure formation, which track the evolution of matter from the early universe to the present, reproduce the observed distribution of galaxies only when dark matter is included. Remove it, and the simulations fail. The galaxies don't form in the right places, at the right times, or with the right properties. The match between simulation and observation is so precise that it has become one of the strongest arguments for dark matter's existence. Yet despite all this evidence, dark matter remains a mystery. We know it's there. We know how much of it exists. We know how it's distributed across the universe, but we don't know what it is. Is it made of particles? If so, what kind? Are they massive and slow-moving or light and fast? Do they interact with each other or only with ordinary matter through gravity? These questions remain unanswered, and answering them has become one of the central goals of modern physics. The most popular hypothesis is that dark matter consists of particles called weakly interacting massive particles, or WIMPs. These hypothetical particles would have mass comparable to heavy atomic nuclei, but would interact only through gravity and the weak nuclear force. The weak force is responsible for certain types of radioactive decay and operates only at extremely short ranges. If WIMPs exist, they would occasionally interact with ordinary matter, but so rarely that detecting such interactions requires extraordinary effort. Experiments designed to find WIMPs are conducted deep underground to shield detectors from cosmic rays and other background radiation. These detectors are filled with ultra-pure materials cooled to near absolute zero and monitored with exquisite sensitivity for the faint signal of a dark matter particle colliding with an atomic nucleus. Despite decades of effort and increasingly sensitive instruments, no confirmed detection has been made. WIMPs, if they exist, remain elusive. Other candidates have been proposed. Axions, for instance, are hypothetical particles much lighter than WIMPs, but predicted to exist in enormous numbers. They would interact even more weakly than WIMPs, making them even harder to detect, but potentially explaining dark matter's abundance. Primordial black holes formed in the early universe rather than from collapsing stars have also been suggested. These would be ordinary matter in a sense, just compressed into objects so dense that they emit no light. Each candidate has strengths and weaknesses, and none have been confirmed. This uncertainty frustrates researchers but also energizes them. Dark matter represents one of the last great unknowns in physics, a phenomenon that is undeniably real but tantalizingly out of reach. Solving it would not just answer what dark matter is, it would reveal new physics, new particles, new forces, and new principles that govern reality at its deepest levels. In the meantime, dark matter continues to shape the universe in ways both subtle and profound. It holds galaxies together, allowing them to rotate without flying apart. It clusters into vast cosmic webs, forming the skeleton upon which galaxies and galaxy clusters hang. It dictates where stars form, where planets orbit, and ultimately where life can arise. Without dark matter, the universe would be unrecognizable. It is the hidden foundation upon which everything visible rests, and yet it remains unseen. A ghost in the machine, felt but never touched, inferred but never observed directly. The rotation of galaxies was the first clue, a discrepancy that refused to vanish no matter how carefully it was examined. That discrepancy opened a door to a universe far richer and stranger than expected. A universe where the visible is the exception and the invisible is the rule. The story does not end with simply accepting that dark matter exists. Acceptance is only the beginning. Once physicists acknowledged that the universe contained this invisible substance, The next challenge was understanding its properties in enough detail to predict how it behaves, where it concentrates, and why it arranges itself the way it does. This required moving beyond observation and into simulation, modeling the universe from its earliest moments forward to see if theory could reproduce the reality we observe. Cosmological simulations are among the most computationally demanding tasks in all of science. They begin with the conditions of the early universe, just moments after the Big Bang, when the cosmos was a hot, dense, nearly uniform soup of particles and energy. Tiny fluctuations in density, seeded by quantum effects during inflation, provided the initial variations from which all structure would eventually grow. These fluctuations were incredibly small, variations of only 1 part in 100,000, but they were enough. As the universe expanded and cooled, gravity began to amplify these fluctuations. Regions slightly denser than average attracted more matter. Regions slightly less dense lost matter to their denser neighbors. Over time, the contrast grew. Density peaks became denser still, while voids became emptier. This process, called gravitational instability, is straightforward in principle but extraordinarily complex in practice, because it involves billions of particles interacting over billions of years across a universe that is simultaneously expanding. Dark matter played the leading role in these early stages. Because it did not interact with radiation, it could collapse unimpeded. Ordinary matter, still tightly coupled to photons, experienced pressure that resisted collapse. This meant dark matter clumped first, forming gravitational wells that ordinary matter would later fall into. By the time the universe had cooled enough for ordinary matter to decouple from radiation, an event known as recombination, dark matter had already established a framework of structure. Galaxies would form within this pre-existing scaffolding. Simulations that include dark matter reproduce the observed universe with stunning accuracy. They predict the formation of a cosmic web, a vast network of filaments and sheets of dark matter connecting galaxy clusters. Observations confirm this structure. Galaxies are not randomly scattered across space. They line up along filaments, cluster at intersections, and avoid the vast voids in between. This pattern emerges naturally from simulations that include dark matter, but fails to form in simulations that rely on ordinary matter alone. Within individual galaxies, dark matter forms extended halos that surround and dwarf the visible components. These halos are not uniform. They are densest at the center and gradually thin out with distance, following a profile that simulations predict and observations confirm. The rotation curves that first revealed dark matter's existence are direct consequences of these halo structures. Stars orbit within a sea of dark matter, feeling its gravitational pull even though they never directly interact with it. The distribution of dark matter within galaxies also influences their evolution. Mergers between galaxies, for instance, are common events in cosmic history. When two galaxies collide, their dark matter halos merge first, creating a combined gravitational field that reshapes the visible components. Stars may be flung into new orbits, gas clouds may collide and ignite bursts of star formation, and the overall structure of both galaxies may be transformed. Simulations of these mergers require dark matter to explain the outcomes. Without it, the dynamics simply don't match what telescopes observe. But dark matter is not just about galaxies. It governs the universe on the largest scales as well. Galaxy clusters, which contain hundreds or thousands of galaxies bound together by gravity, are dominated by dark matter. The visible galaxies account for only a small fraction of the total mass. Most of the mass is dark matter, with hot gas filling the space in between. This gas emits X-rays, allowing astronomers to map its distribution and infer the total mass of the cluster. The results consistently show that dark matter outweighs both the gas and the galaxies combined. One of the most remarkable features of dark matter is its stability. Unlike ordinary matter, which can radiate energy and lose momentum through electromagnetic interactions, dark matter cannot cool or collapse in the same way. It remains diffuse, forming extended halos rather than condensing into compact objects. This property prevents dark matter from collapsing into stars or planets. It exists as a background presence, shaping the universe gravitationally but never directly forming the structures we see through telescopes. This also means dark matter is incredibly pervasive. It fills the space between galaxies, the space within galaxies, and even the space within our solar system. Right now, as you read this, dark matter particles are passing through you, through the Earth, and through everything around you. They interact so weakly that they leave no trace, but their collective influence on the cosmos is undeniable. Despite its pervasiveness, detecting dark matter directly remains one of the greatest challenges in physics. The problem is straightforward. Dark matter particles, whatever they are, interact so rarely with ordinary matter that catching one in the act requires extraordinary patience and precision. Dozens of experiments around the world are dedicated to this task, each employing different strategies and technologies. Direct detection experiments aim to observe the recoil of an atomic nucleus when struck by a dark matter particle. These experiments are typically located deep underground to shield them from cosmic rays, which could produce false signals. Detectors are filled with ultra-pure materials, often liquefied noble gases like xenon or argon, and cooled to extremely low temperatures to reduce thermal noise. Any interaction with a dark matter particle would produce a tiny flash of light or a faint electric signal which sensitive instruments would record. Despite years of operation and increasingly sensitive detectors, no confirmed dark matter signal has been found. This does not mean dark matter doesn't exist. It means that if dark matter particles interact with ordinary matter at all, they do so even more rarely than the most optimistic predictions suggested. The lack of detection narrows the possibilities but does not eliminate them. It simply means the search must continue with even more sensitive instruments and longer observation times. Indirect detection takes a different approach. Instead of waiting for dark matter to interact with a detector, these experiments search for the products of dark matter particles annihilating or decaying in space. If dark matter particles occasionally collide with each other and annihilate, they could produce ordinary particles like photons, neutrinos, or antimatter. These products would travel through space and could be detected by telescopes or particle detectors. Some of the most sensitive searches look for excess gamma rays coming from regions where dark matter is expected to be dense, such as the center of the Milky Way or nearby dwarf galaxies. Others search for anomalies in cosmic rays, high-energy particles that constantly bombard Earth from space. A few experiments have reported tantalizing hints, such as an excess of positrons or an unusual gamma-ray signal, but none have been confirmed as definitively coming from dark matter. Alternative explanations, such as pulsars or other astrophysical sources, remain plausible. Collider experiments offer a third strategy. If dark matter particles have mass in a certain range, they might be produced in high-energy collisions at particle accelerators like the Large Hadron Collider. These experiments smash protons together at nearly the speed of light and look for evidence of new particles in the debris. Dark matter particles, if created, would escape the detector without interacting, but their presence could be inferred from missing energy and momentum in the collision. So far, no collider has produced evidence of dark matter particles, but the searches continue, pushing into new energy ranges and exploring new theoretical possibilities. Each negative result refines our understanding, ruling out certain masses and interaction strengths and guiding future searches. The challenge of detecting dark matter is compounded by the fact that we don't know what we're looking for. If dark matter is made of WIMPs, the experiments currently running have a good chance of finding them, but only if WIMPs interact strongly enough and have the right mass. If dark matter is actions, entirely different experiments are needed, one sensitive to extremely faint signals from vast numbers of ultralight particles. If dark matter is something else entirely, something not yet imagined, then current experiments might never find it, no matter how long they run. This uncertainty is both frustrating and exciting. It means the discovery of dark matter, when it comes, could be genuinely revolutionary. It could reveal new particles, new forces, and new principles that fundamentally alter our understanding of the universe. Or it could show that the universe operates in ways we haven't yet conceived, requiring not just new experiments but new ways of thinking about reality itself. In the meantime, the evidence for dark matter continues to accumulate. Every observation, from the rotation of galaxies to the structure of the cosmic microwave background, points to the same conclusion. The universe contains vast quantities of invisible mass that interacts only through gravity. This mass shapes galaxies, clusters, and the cosmos as a whole. It is woven into the fabric of space-time, influencing everything we see without ever revealing itself directly. And this brings us to a profound realization. The universe is not what it appears to be. The stars, galaxies, and nebulae that fill our telescopes are not the main actors in the cosmic drama. They are only the visible surface, the glowing exceptions in a universe dominated by darkness. Dark matter is the foundation, the unseen majority, the substance that makes everything else possible. Without dark matter, galaxies would not rotate the way they do. They would have torn themselves apart long ago, scattering their stars across the void. Without dark matter, galaxies would not have formed in the first place. The early universe would have remained smooth and featureless, a diffuse cloud of gas expanding into emptiness. Without dark matter, the cosmic web would not exist, galaxy clusters would not hold together, and the universe would look nothing like what we observe. In this sense, dark matter is not a footnote to the story of the cosmos. It is the story. The visible universe is a consequence of dark matter's presence, a thin layer of light draped over a vast, invisible structure. We live in a universe where what we can see is a minority, a small fraction of what exists. The rest is hidden, interacting with us only through the one force it cannot avoid: gravity. This realization is humbling. It reminds us how much we still don't know, how much of reality remains beyond our senses and our instruments. But it is also empowering. because even though we cannot see dark matter directly, we can study it. We can map its distribution, measure its effects, and use those measurements to learn about the universe in ways that would be impossible otherwise. Dark matter is not a barrier to understanding. It is a window into a deeper layer of reality. The rotation of galaxies was the first clue, a simple observation that refused to fit into the existing framework. That observation led to one of the most profound discoveries in the history of science, the realization that the universe is far stranger, far richer, and far more complex than we ever imagined. And the search for dark matter continues, driven by the knowledge that somewhere in the darkness, answers are waiting to be found. Yet even as we accumulate evidence and refine our models, a shadow of doubt remains. Not about whether dark matter exists, the evidence is overwhelming, but about whether we're asking the right questions. Because science has a history of surprises, moments when the accepted explanation turned out to be incomplete or entirely wrong. For decades, astronomers believed the universe was static and eternal. Then Edwin Hubble discovered it was expanding. For centuries, physicists thought light required a medium to travel through. Then, experiments proved the ether didn't exist. Each time, the shift required abandoning a deeply held assumption. Could dark matter be another such assumption? Could there be a different explanation for galaxy rotation curves, one that doesn't require invoking invisible mass? This question has driven a small but persistent group of physicists to explore alternative theories, modifications to gravity itself that could explain the observations without dark matter. The most well-known alternative is called modified Newtonian dynamics, or MOND. Proposed in the 1980s by physicist Mordechai Milgram, MOND suggests that Newton's laws of motions and gravity break down at extremely low accelerations, the kind experienced by stars at the edges of galaxies. In this view, gravity doesn't weaken with distance quite as much as Newton predicted. At large scales, it falls off more slowly, providing extra pull that keeps stars bound to galaxies without requiring unseen mass. MOND has some impressive successes. It accurately predicts the rotation curves of many spiral galaxies with remarkable precision. It does so with fewer free parameters than dark matter models, which require assumptions about how dark matter is distributed. For individual galaxies, MOND often fits the data better than dark matter, and it does so without invoking any invisible substances. But MOND also has serious problems. It struggles to explain galaxy clusters where the discrepancy between visible mass and total mass is even larger than in individual galaxies. It cannot account for gravitational lensing observations, which show that mass is concentrated in places where no visible matter exists, and it has difficulty reproducing the structure of the cosmic microwave background, which depends sensitively on the balance between ordinary matter, dark matter, and dark energy. Moreover, MOND is not a complete theory. It modifies the behavior of gravity but does not explain why gravity should behave differently at low accelerations. It lacks the theoretical foundation that general relativity provides for standard gravity. Without that foundation, it feels more like a mathematical trick than a fundamental principle. Other modifications to gravity have been proposed, some more sophisticated than MOND. These theories attempt to incorporate the successes of general relativity while introducing new terms or fields that could explain galaxy rotation without dark matter. Some introduce additional dimensions of space. Others propose that gravity is mediated by multiple particles rather than just one. A few suggest that the fabric of space-time itself has properties we haven't yet discovered. Each of these theories makes predictions that can be tested, and many have been ruled out by observations. The bullet cluster, for instance, is particularly problematic for modified gravity theories. The clean separation between the locations of ordinary matter and gravitational mass is exactly what dark matter predicts, but difficult to explain if gravity alone is responsible. Gravitational lensing maps show mass concentrated where dark matter should be, not where the visible galaxies are, a pattern that emerges naturally from dark matter models but requires special conditions in modified gravity. The cosmic microwave background is another challenge. The precise pattern of fluctuations in the CMB depends on the composition of the universe at the time the radiation was emitted. Models that include dark matter fit the data extraordinarily well. Models that modify gravity struggle to match the observations without adding additional components that begin to look suspiciously like dark matter under a different name. Despite these difficulties, alternative theories continue to be developed and tested. This is healthy for science. Competition between ideas sharpens understanding and prevents complacency. If dark matter is real, then modified gravity theories will eventually fail enough tests to be discarded. If modified gravity is correct, then dark matter experiments will continue to find nothing, and the theory will gain strength through the absence of alternatives. Either way, the process of testing and refining pushes the field forward. But for now, the weight of evidence favors dark matter. It explains not just galaxy rotation curves, but a wide range of independent observations, from gravitational lensing to the formation of large-scale structure to the cosmic microwave background. No modified gravity theory has yet matched this breadth of success. And while dark matter has not been detected directly, that absence is not evidence of its non-existence. Many particles predicted by theory were detected long after their theoretical discovery. The Higgs boson, for instance, was proposed in the 1960s but not observed until 2012. Neutrinos were predicted in 1930 but not detected until 1956. Patience and persistence are part of the process. The search for dark matter also benefits from technological advances. Detectors are becoming more sensitive. Telescopes are observing deeper into space and further back in time. Computational simulations are growing more sophisticated, incorporating more physics and resolving finer details. Each improvement brings new opportunities to test the dark matter hypothesis and rule out alternatives. One of the most promising frontiers is the study of dwarf galaxies. These small galaxies are dominated by dark matter even more than large galaxies like the Milky Way. In some dwarf galaxies, dark matter outweighs ordinary matter by factors of hundreds or even thousands. This makes them ideal laboratories for testing dark matter models. Any deviation from predictions would be more apparent in dwarf galaxies than in larger systems where ordinary matter contributes more to the total mass. Observations of dwarf galaxies have already revealed intriguing features. Some contain fewer stars than simulations predict, a problem known as the missing satellites issue. Others have dark matter distributions that appear smoother than expected, while simulations tend to produce more concentrated cores. These discrepancies do not disprove dark matter, but they suggest our understanding is incomplete. Perhaps dark matter interacts with itself in ways we haven't accounted for. Perhaps the process of galaxy formation is more complex than current models capture, Or perhaps there are subtleties in how dark matter behaves that require new physics to explain. Another frontier is the search for ultra-light dark matter, particles so light that they behave more like waves than particles. These could form diffuse clouds that permeate galaxies, creating interference patterns and subtle effects that might be detectable through precise measurements of stellar motions or pulsar timing. If dark matter is ultra-light, the detection strategies would be entirely different from those designed for WIMPs, requiring new kinds of experiments and observations. There is also growing interest in the possibility that dark matter is not made of a single type of particle, but rather a complex assortment. Much like ordinary matter includes protons, neutrons, electrons, and a zoo of other particles. If dark matter has its own periodic table, its own chemistry, its own interactions, then the universe could be far richer than we've imagined. This dark sector could include dark photons, dark atoms, even dark forces that govern interactions among dark matter particles. Such a sector would be invisible to us but could leave subtle imprints on the structure and behavior of galaxies. Testing these ideas requires creativity and collaboration across disciplines. Astronomers observe galaxies and map dark matter distributions. Particle physicists build detectors and search for signals. Cosmologists simulate the universe and compare predictions to data. Theorists propose new models and calculate their consequences. Each group contributes a piece of the puzzle, and together they're slowly building a picture of what dark matter is and how it shapes the cosmos. The stakes are high because understanding dark matter is not just about solving a single mystery. It is about understanding the universe at the most fundamental level. Dark matter connects particle physics, cosmology, and astrophysics in ways that few other phenomena do. Discovering what it is made of could reveal new laws of nature, new particles, and new interactions that extend the standard model of particle physics, which has been the foundation of our understanding for decades but is known to be incomplete. And then there is the philosophical dimension. If dark matter is real, then the universe is profoundly different from what our senses suggest. Reality is not limited to what we can see, touch, or measure directly. It includes layers that interact with us only through gravity, layers that shape the world we inhabit but remain forever out of direct reach. This realization changes how we think about existence itself. It reminds us that human perception is limited, that our instruments extend our senses but still capture only part of the whole, and that the universe is under no obligation to reveal itself in ways we find intuitive or convenient. At the same time, it demonstrates the power of human reasoning. We cannot see dark matter, but we know it's there because we can follow the logic of physics to its conclusion. We observe effects, measure them carefully, and infer causes even when those causes are invisible. This is the essence of science, the ability to understand what cannot be directly perceived by building models, testing predictions, and refining theories in light of evidence. The rotation of galaxies was a small crack in the edifice of our understanding. That crack widened as evidence accumulated, eventually revealing that the universe is not what it seemed. And now, as we stand at the frontier of knowledge, we're left with questions that future generations will answer. What is dark matter made of? How does it interact with itself and with ordinary matter? What role did it play in the earliest moments of the universe? And what will it do in the distant future as the cosmos continues to expand? These questions drive research forward, pulling scientists into deep mines, remote observatories, and cutting-edge laboratories. Somewhere in the data, in the faint signals and subtle patterns, answers are waiting. And when those answers come, they will not just solve a puzzle. They will open doors to understanding we cannot yet imagine, reshaping our picture of reality in ways that ripple through every corner of physics. For now, we know this. Galaxies rotate without flying apart because they are embedded in halos of dark matter. This invisible substance provides the gravitational glue that holds them together, allowing stars to orbit stably for billions of years. It is the scaffolding upon which the visible universe is built, the foundation that makes everything else possible. Without it, there would be no galaxies, no stars, no planets, and no life. In this sense, dark matter is not a mystery to be feared or dismissed. It is a reminder of how much remains to be discovered, how much richness lies hidden beneath the surface of what we can see. The universe is vast, strange, and full of surprises. And one of the greatest surprises of all is that most of it is invisible, woven into the fabric of space itself, shaping the cosmos in ways we're only beginning to understand. If you enjoyed learning about this cosmic mystery, don't forget to leave a like and subscribe. It makes a huge difference and helps the channel grow. The universe holds countless secrets, and together we're going to keep exploring them.